Welcome to The Explainer. Today, we're going to pull back the curtain on some of the engineering magic that makes your internet feel so fast. We're breaking down two really key techniques, caching and a protocol called HTTP/2 that are working hard behind the scenes every single time you go online.
Have you ever noticed this? You're on campus with thousands of other people, yet the Wi-Fi just feels snappier than what you have at home. So what's the deal? Well, the answer isn't just about having a bigger pipe to the internet. A lot of the time, it comes down to some really clever engineering that's trying to predict what you need and get it to you before you even ask. Today, we're going to unpack the math behind it all.
Okay, so here's our game plan. We'll kick things off with a classic cache scenario, and then we'll actually calculate its performance. From there, we'll jump into something called the HTTP/2 delivery race, compare two different styles of delivery, and then wrap it all up with the key things you need to remember.
First up, let's set the scene. Imagine we're on a big university campus. The network admins there are using something called a proxy server to try and speed things up for everybody. And you know what? It's a super common and really effective way to do it.
The tool they're using is a proxy cache. Now, the best way to think about this is like having a small local library right there on campus. Instead of every single student having to order the same popular textbook from a warehouse halfway across the country, the campus library just keeps a bunch of copies right there on the shelf. In the digital world, that's exactly what a cache does. It stores popular stuff locally so you can get it way faster.
So this whole system really boils down to two possible outcomes. If the file you want is already in that local library, we call that a cache hit, and that is super fast. But if it's not there, that's a cache miss, and the server has to go all the way out to the wider internet to grab it, which, you guessed it, is a lot slower. The name of the game is to get as many hits as you possibly can. And here's the actual data for our little scenario. We've got three different files, objects A, B, and C, that students are requesting all the time. You can see their sizes and how popular each one is per hour. Now, the crucial part is this. Our campus cache has copies of A and B, so those are potential hits. But it doesn't have that huge file, object C. That one's always going to be a miss. So, you might be asking, how much of a difference does this cache actually make? Is it worth it? Well, let's do the math and see what the real-world performance gain actually looks like for this university network.
To figure out how well our cache is doing, we use a simple metric called the cache hit ratio. All it is the percentage of requests that our local cache was able to handle all by itself. The higher this number, the better the cache is performing. It's kind of like its report card.
And calculating it is really pretty straightforward. First, we just add up all the requests that were successful hits, so that's all the requests for object A plus all the requests for object B. Then we take that number and divide it by the total number of requests for all the objects, A, B, and C combined.
And boom, there's our answer. The cache hit ratio is 83.3%. Think about that. That means more than 8 out of every 10 requests from students are served instantly from the local network. They never even have to go out to the university's main and probably much slower internet connection. That's a huge win.
Looking at it this way, the impact is just so clear, right? The huge majority of requests are these super efficient cache hits. It's only that small slice of misses that actually have to go out and generate traffic on the main internet line.
But what does this mean in terms of, actual data? We can figure that out too. All we have to do is multiply the size of each cached object by the number of times it was requested in an hour. This will tell us exactly how much data the cache is saving from being downloaded over and over again.
And look at that total, 1,560 megabytes per hour. That is over 1.5 gigs of data times every single hour that the university doesn't have to pull down from the internet. This frees up so much bandwidth, it saves money, and it makes the entire network feel faster for everyone.
All right, let's totally switch gears. We just saw how caching saves a ton of data. Now, let's look at how we can deliver data more intelligently using a modern web protocol called HTTP/2. This is less about saving data and more about the user's perception of speed.
The key idea we need to understand in HTTP/2 is called interleaving. So instead of the old way, where a server would send one entire file and then move on to the next one, HTTP/2 is much smarter. It breaks all the files up into these tiny little pieces called frames. Then it can send a frame from file 1, then a frame from file 2, then another from file 1, and so on, basically mixing them all together in one continuous stream.
So let's put this to the test. Imagine a server has to send two objects, A and B. We're going to have a little race between two delivery strategies.
the old school way, sequential, and the new HTTP/2 way with interleaving.
In the old sequential delivery model, the server sends all of object A first. Only after A is completely finished its journey, which happens at the 8-millisecond mark, can it even start sending object B. B has to wait its turn. But with interleaving, the server is like a master multitasker. It sends the first little piece of A and then immediately sends the first little piece of B. This means your web browser starts receiving both files at almost the exact same time.
And here is the big payoff. To get just the very first piece of object B, the old sequential method takes 12 milliseconds, but interleaving, it delivers it in just 8. Now, even though the total download time for everything is the same, starting to see that second part of the web page 4 milliseconds earlier makes the entire site feel faster and way more responsive. It's a trick that works on our brains.
So, after running through all those scenarios and all those numbers, what are the big ideas you should really walk away with from all this?
It really comes down to two main pillars of a faster web. First, you've got caching, which attacks the problem with pure efficiency. It saves bandwidth, it reduces server load, all by just keeping stuff closer to you. And second, you have intelligent delivery, like HTTP/2's interleaving. This attacks the problem from a human psychological angle, making sites feel faster, which, at the end of the day, is often just as important.
These two techniques are absolutely fundamental to why our modern internet works as well as it does. And that kind of leaves us with one final thought. As we keep pushing towards crazier applications, immersive streaming, and virtual worlds, what new tricks are we going to have to invent to make sure tomorrow's internet feels just as fast?